Oh, hi everyone. Thanks so much for showing up for your math learning. I am Mr. Jennings. You ever feel like so tired that you like take one sleep and you're like, nah, that didn't do it. And then the next day you take another sleep and you're like, oh, there I am. I am on the other side of the second sleep. So I'm happy to see you today. Okay, let's go. So we are looking at applications of sinusoidal functions. Really, this is the most repeat of all of our stuff, which is great news. We're going to get a chance to take a look at some of the tips and tricks we've learned so far and apply them in visualizable contexts. So this is where the tire can hit the road, as it were. So we're going to see the relationship between sine and cosine functions in context and look at their properties and work on the equations of sine and cosine functions in context. Essentially, all of our applications are sine and cosine because this thing shows up in nature, and you'll notice like this thing doesn't really show up in nature, right? When do we see this? These like inverse ones, that's too weird. So anyway, if you need some review, there's some prescribed in the D2L, but let's talk about where we see these things. Basically, anytime number go up and then number come down and then number go up again, in a predictable, repeatable pattern, you can apply the mathematics of sine and cosine. So weather is a big one. This is related to daylight or even like weather. We have our main metaphor, like where you have sine starts in spring, goes towards summer, goes through autumn, and then hits winter and comes back to spring. Like if you really think about that as a metaphor, it's very useful to have something to visualize these 4 key points that are separated by your 1/4 period. So weather and day length and things are all connected to that. You could also use the day, and so daylight, like this would be midnight, and this would be noon, and this would be like sunrise and sunset. There. So you could use those to memorize your different points along the period of these things. The motions of pendulums or springs or things that go back and forth can be modeled with periodic functions. Anything that's moving in a circle, which could be from the atomic to the astronomic to the Ferris wheel. We're going to look at Ferris wheels today, everybody. Hey, Ferris wheel's my favorite. Okay, even your blood pressure where it goes or whatever your heartbeat does. These are periodic functions as well, and that could be given as the sum of a series of sine waves would produce that type of wave function. And it's complicated, that math. Go to university, study it. Let me know how it goes. Okay, so let's keep going. So, in the first example that you have, this type of example is we give you the equation and you do stuff with the equation. Okay, so that's like level 1. Next level we're going to look at is you have to build your own equation. So, we have h of t is equal to this. Here's our a value. So, okay, a is minus 20. So we have an amplitude of 20, and we are starting with negative cosine. Negative cosine, just starting with a quick sketch in my mind, starts in winter, starts at midnight, and goes up. That's negative cosine. That's one period of negative cosine. So I'm just having that in my mind. And then here, k value. Kenzie, it's going to be fast. Okay. K value is, well, if I have the k value, wait, I know the k value, but I want the period. The period is given by 2 pi over k. So let's work on that. 2 pi, there's my fashionable pi with 2 pi, over pi by 12. When I keep flip change, that's 2 pi multiplied by 12 on pi, which is cancel, cancel. Fancy way of saying 24. So every 24 seconds, this thing completes a full period. Cool. So then our 1/4 period is really easy to get. It's 6. So 6 equals the 1/4 period. In other words, the distance between midnight and sunrise, or spring and summer, etc., etc. Okay, and then we have the horizontal axis over here, C, given by 22. So from that, I'm going to take that and put it together with my amplitude to get horizontal axis equals 22. The max is at 42, and the min is at 2. And then the only thing left to really discuss is, when do I get on this Ferris wheel? Like, when do I start? Well, plus 2 there. I wonder, what's that going to do to my function? Yeah.
Phase shift to negative direction.
Yeah, so it's going to shift this starting thing to that way. How much of a period is that?
1/12.
Good. So we're going to be at like pi by 12 into negative cosine. So that's 1/12 of the period in. So that's going to be our initial value. Okay, so we've got a lot of information already. So one thing that I might imagine, if I really want to consolidate my learning, is this giant Ferris wheel that hovers 2 meters above the ground. Okay, and there's the ground there. And not only that, but there's like a platform that comes up, and we get on the platform. We get on above the minimum, right? Because we shifted it over that way, so we're getting on like up here, right? Because it's going to be shifted when I graph this thing. And what else to say? Well, it's 1/12 of a circle. Gee, if I only had something that was a really useful way to visualize 1/12 of a circle. Yeah, so where would I get on this Ferris wheel on the clock? At what o'clock? If you imagine that the Ferris wheel is the minute hand, and it moves in the direction that the minute hand moves, aka clockwise, then you'd be getting on at 7. Okay? Just 1/12 above the minimum. Make sense? So we'll call that like right here. We get on this thing over there, and we go up that way. This is our t equals 0 moment right there. Okay, and then we'll hit the minimum later, and et cetera, et cetera. So now let's graph it. It's about time. We should graph it. It says sketch one cycle of the height function. Don't mind if I do. Here we go. Put our x-axis down there. Why is it like organized slightly oblique to the page? It's a sketch. Okay, it's a sketch. Things are going to get sketchy here. All right, so we will want that like 2 line. So let's put that along there. There's our minimum. That's y, or I should say h equals 2, because we have h of t, not, we can say call this the h-axis, and this the t-axis time. So this is h equals 2. And then we'll have our midline somewhere around here. Okay, and then our maximum somewhere around there. And this is h equals 22, and h equals 42. Okay, now we start with that function that would have started there in winter and gone up, hit the maximum, come down. This is like the invisible function that we're going to shift. I'm going to do just a little bit more of it. And then we're going to shift it all back this much, so that, as Connor points out, we end up with our starting position back there at h at -2, which would give us a minimum, which is like the time before time started. And then this comes up. And it does everything just a little bit before it did those things like that. Maybe we join it when time is really real, over here like this. And then we're just left to find some of the key points. So let's go ahead and do that. Clearly, one of our key points is our starting position. So that's like h at 0. And to do that, I would just evaluate. Okay, so we're just going to evaluate to find out that point. So we're going to copy out h of t equals, just copy it out, -20 cosine of pi by 12 t plus 2, all plus 22, and then input 0. And so that gives us h at 0 equals minus 20 times the cosine of pi by 12 times 0 plus 2, that's 2, plus 22. So this is asking us to evaluate, that's the argument of cosine. It's asking us to evaluate cosine of pi by 6. Hey, we can use our unit circle to visualize that. So cosine of pi by 6 is what exact value? Adjacent over hypotenuse, yeah?
Oh, what is that?
I visualize my unit circle. Pion, pion. I have pi by 6 here. That's the 30-degree triangle. That's 1, that's 1/2. That's root 3 on 2. Cosine. Okay. So I evaluate that. So I do minus 20 times root 3 on 2, which is to say negative 10 root 30 plus 22. And then we want an approximate answer to what that is. It's that, 4.7. Okay? That's a calculator question. 4.7 meters. Okay? So this point here, we could put it on as this, as the y value, if we wanted to keep it exact. But if someone said, how high do you reckon they're getting on their Ferris wheel? And you tell them, I suspect, actually no, I don't suspect, I know that they precisely get on at negative 10 root 3 plus 22 meters. That them there person asking you that them there question is going to look at you real strange. So I would give 4.7 meters here. This is an application. Okay. If you go to a hardware store and try and order this much wire, they're going to look at you weird. So, okay, so it's 4.7 meters high. So there it is. So that's the point 0, 4.7. Okay, good. Now, where does it going to cross there? Well, I might want to know that point, that point, that point, and that point. Yes, Mr. Weibel?
Just find your quarter periods.
Just do quarter periods. But do I do quarter periods from here?
No, from the 2.
Yeah, from the minus 2 here.
Mm-hmm.
Right. So the quarter period we noticed was going to be 6. So where's this one going to be in terms of t for time? Yeah, right, 4. Good. So I can put in 4, and then that's where cosine is normally equal to 0. That's this one. So this is easy. That's at 22. Okay? And then I do my next quarter period. This one is at 10, 42. This one is at 16, 22. And this one is at 22, 2. Oh, that's a pretty point. Okay. So there's all of our pretty points on this thing. We got enough. Label all axes and key points. There you go. Okay. The last thing we might do is, do we dare check our work in Desmos? Let's go, everybody. This is our favorite part because, yeah, today I was talking to students and they said, I like it when the math makes sense. And I said, I like that too. But you know what I like even better? And this is true. I like it when the math transitions from making no sense to making sense. That's my favorite. Okay, so we have y is equal to negative 20 cosine of, put it in brackets, pi by 12, multiply this by x plus 2, end the bracket again, add 22. Oh, isn't this just delightful? And then put in your y equals 22 and your y equals 42. And just like go on a magical mystery tour here. Look at that. We nailed them.
Are you able to click on 15 so I can check my work really quick?
15?
Yeah.
What 15? Oh, for the next question.
Like just so I can check.
If when are they at 15 high? I'll just set it here.
15 seconds in, sorry.
Oh, where are they 15 seconds in? Okay, not when they're 15 high. 15 seconds. So we'll just say x equals 15, and this should actually be right there. Yeah, that's 15 and 27.17, blah, blah, blah. Okay. So that is the next question that we're going to. Good. So anyway, it validated our sketch. Let's keep going. What is the height to the nearest tenth of the rider after 15 seconds? Okay, so we are asked to evaluate h at 15, and that's equal to minus 20 cosine of pi by 12 at 15 plus 2 plus 22. Okay, so now that's h at 15 is equal to negative 20 of cosine 17 pi by 12 plus 22. And this is just, since it asks to the nearest tenth, we can just evaluate that. Is it possible to get an exact value here? You're just like, I don't know, can we do some combination of thirds and quarters that adds up to this?
Probably can, but it's less demeaning if you do it a different way.
Yeah, you can. 17 pi by 12 is equal to 9 pi by 12 plus 8 pi by 12. So you'd use a compound angle theorem and work out that this is 3/4 pi plus 2/3 pi. And then you would use your cosine of a plus b and do it that way. But we were just asked to plug and chug. So you just go ahead, and if I'm going to punch that on the calculator, I'm going to punch it from the deepest level first. So I would punch it this way. 17 times pi divided by 12 equals this. This is the exact value of that angle in radians. So I can imagine, okay, 4.45. We started there and we went around that much. Okay, cool. All right, and then I do cosine of that. So I'm going to go trigonometry, take the cosine of that angle. I'm in radians, right? No, I'm in degrees. No, don't do that. Go back to radians, undo, clear. 17 times pi divided by 12. This many radians. Take the cosine of it. There we go. We got that negative number. Multiply it by 20, but it's negative. It's that, and then add that to 22, and I get that 27.176. Yay, 27.176. My calculator and this calculator agree. Good, that's all we do there. All right, next. If we wanted to know when in the first cycles the rider is at a height of 26 meters above the ground, these are trickier. So in these cases, we might write out h of t is equal to, we want to find the t value when this whole thing is equal to 26. Well, what is it? Well, it's equal to minus 20 cosine of pi by 12 multiplied by t plus 2 plus 22. And then this is a tangled Gordian knot of Bedmus. And we're just going to untangle it outer layer towards the inner layer. Just peel the onion one layer at a time. First layer that I'm going to take away is the loosest. Take away that addition and subtraction. That's pretty loose. So we subtract that from both sides and we get 4 is equal to minus 20 cosine of pi by 12 multiplied by t plus 2. That's the argument of cosine, so I'll put it all in big brackets so that that's clear. And this is gone. It became 0, so that's gone. Next layer that's the easiest to peel away is the multiplication, so we're going to divide both sides by 20. Okay. And so then we get 4 divided by minus 20 is minus a fifth is equal to cosine of pi by 12 multiplied by t plus 2. All right. And next, we now have cosine is now our loosest layer of bedmus. So we now inverse cosine both sides. Like that. So to do this, you can just punch on calculator. Just go ahead and straight punch away. But visualize on your unit circle will save you so many errors and also help refine your thinking. Negative 1/5. When cosine is negative 1/5, cosine is negative, so it's over this way. Okay, it's in these two quadrants when cosine's negative. And so 1 would be like that there. This is 1. And then we have this very tall angle where that's 5. Okay, so there's that one where cosine is negative 1/5, and this one where cosine is negative 1/5. So it looks like ever so slightly more than 90, maybe somewhere around 100 degrees, and somewhere around like 260 or something like that would be my guess in degrees. And radians, oh, I don't know, that's what, about 2? Maybe? Somewhere around there, a little less than 2, something like that. Okay, all right, so let's go. These are the two angles we're looking for. Why do we need 2 angles? Why are we looking for 2 solutions here?
Because it goes in the circle, it should, oh, sorry.
It does say the first 3 cycles. And if we just remember our sketch, oops, call that the horizontal axis. So here's our sketch, just very briefly, going to recreate it. That's the noise people make on Ferris wheels. Okay? And then we are interested in the times where they're 26 meters above the ground. So these times. Oh, there will be 6 of them, 2 per cycle. Okay? Or you visualize your Ferris wheel and you're saying, when are they that high? 2 times per cycle, on the way up and on the way down. It would be similar to saying, which month in Collingwood is the day length 14 hours? Well, one of the later months in the spring and one of the earlier months in the fall, or well, it'd be later month in the summer, would be 14 hours. It's like not the longest day length we ever get, but it does lengthen up. Okay, so anyway, so that's why we need 2. And the unit circle gives you both of them, and so does your cast rule. CAST. Cosine is positive here and here, but we have a negative cosine, so this is where we find our solutions. Okay, so now, once you've done, that's all very brief, right? In your mind, you're like, I'm going to briefly visualize unit circle so that I understand how my reference angle is related here. So then, we're going to go to the calculator and say clear, and we say negative 1 divided by 5 is, wouldn't you know it, negative 0.2. I do second function, inverse cosine of that, and I get 1.77. And I ballpark the radians at 2, and so there it is, 1.77. Not that great a ballpark, but close enough. Okay, so that is the first one that we get. That's here, you know, like that. If I wanted this one, how am I going to get that? Yeah. Huh? Yeah. Well, if I add a cycle, like if I add a cycle, one meaning of that might be to like go from here and be there again. But that's like saying I can get you this solution and then that solution. But I want to get this one over here, which is symmetrical around the maximum here, like it's symmetrical around this. But what I would do is, we just found this piece of information. I'll show you the piece of information we just found, if the eraser works. That this is 1.77 radians. We know this is negative 1.77. So the easiest way to find that, but positive, because we don't necessarily want the negative solution. That's like finding this point. Yeah, 2 pi minus that. Yeah. So I do 2 pi minus 1.77. Yeah? Not in this case. So that's a great idea, but only if it's like a spring, summer, fall, winter point that naturally are spaced out by quarter periods. In this case, because we're like approaching summer this way, we might be just like, you know, an 11th period or something like that, something that's not a multiple of a quarter. around the symmetry point. So here we have to use that idea of the related acute angle and find that other solution, because this one is not like on a nice exact quarter period point. Okay, so here, when I do this, what I find is that this is 1.77, or, and then we're going to do this. Let's just flip its sign. So we have this -1, and we're going to add 2 times pi, and then that gives us 4.511. So what we've done there is found this angle and that angle. Cool. Which is to say, these two solutions. Now, so that is all equal to, let's go back to green because for some reason I'm in blue. This is equal to pi by 12 times t plus 2. Okay, that's what that's equal to. So now, at that point, we're going to consider these separately. So this is 1.77 is equal to pi by 12 times t plus 2. We are going to multiply both sides by 12 on pi to peel away that layer of bedmas. 12 on pi. Oops, that's not a pi, that's a 12. Multiply both sides by 12 on pi. Okay. So there's that. Oh, wait. We'll just go back to that number. Minus 2 times pi equals that. And then flip its sign back to positive. Okay, so I've got that number, the exact one on my calculator. Well, the very approximate, very good approximate on my calculator. Times 12 divided by pi equals 6.769. So 6.769 is equal to t plus 2. Because when I multiply by the reciprocal, it cancels, 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 cancels. So it does successfully isolate that. Next is just to subtract 2 from both sides. And then we get 4.769 equals t. That's the first one. Okay, just subtract 2 equals 4.7691. All right, let's check Desmos right now just to see how we're doing. So we are interested in where y is equal to 26, I think we are looking at, right? Yes, 26. So let's just set y equals to 26 here. And our first one is 4.769, matching perfectly what we found in the other spot. Next, we're going to want this point over here, 15.23. And yeah, so yes, no quarter period help available here. We just have to use this number, 4.511. So 4.511. We are going to multiply that by 12 on pi. So anyway, I will work on it this way here. I'll write it out. If you start with 4.511, this number here is equal to pi by 12 multiplied by t plus 2. Then we're just going to peel away our bedmas by multiplying by 12 on pi. Multiply by 12 on pi. The trick is if you're multiplying by a fraction, just multiply by the reciprocal and it cancels out the fraction. So let's do that. Times 12 divided by pi is equal to this number. And so 17.23 is equal to t plus 2. So we expect this to be 15.23 is equal to t. Okay? Minus 2 equals 15.231, 2307. So then we go back to Desmos and verify, and it's 230, 231, 2308. 15.2308, really? Oh, I was working with a rounded version on my page. That's why I had a slightly different thing on my calculator. But it's essentially the same thing. We're fractions of seconds of error based on my rounding. Okay, so there's our first two solutions. Now, that's the hard part. Getting the next 4 solutions that come from the following 2 cycles. What do you suppose we do? Add a period to each one. Yeah, so we have this one. and then 28.77, and then add another 24 to that, so that's 52.77 seconds. Okay, there, and then this one, add 24, so that's 39.23, and then add another 24, and that's 63.23, and there's your 6 solutions. You would write it out far more beautifully than I am here, because you care about your marks. I'm just kidding. I will write it out. There, that's a sentence for full marks.
Will you ever give like an inverse question?
Inverse question. This is kind of the inverse. Like you see how this one is just evaluate, like I just plug in the x value and then I just evaluate across.
No, like the inverse of like secant or cosine.
So a reciprocal one,
Yeah.
an application one.
Yeah.
Like the path of a UFO is modeled by secant. It blips into existence, does a dive, abducts someone, zooms up to infinity and blips out of existence before returning on the south side of the globe. Like that.
Yeah.
Will I do that? Now I might. This is a really good idea. No, I will not. Because those functions don't tend to have applications, like modeling things in the world. I mean, they're useful mathematically, but they don't like, oh, the waves out there are like a secant function. Whoa, wait, what? That's some kind of weird. I want to ask like an AI to show me what those waves would look like and what the physics of that universe would be that would create such waves, right? You can go out onto the bay today and say, what would the amplitude be? What would the period be? And the phase shift is entirely dependent on when I start observing it, right? And then what's the water level like? That's my C value, right? Like those waves are literally sums of sine waves. Okay, so try those problems, and I'm going to leave you alone until tomorrow when I do more teaching. Otherwise, thanks for hanging with me. You got more questions about this example, yeah?
Oh, I was just wondering if there's spare paper over there.
Yeah, sure.
Thanks.